Okay, so let's try this problem. I'll have to sketch it up first. I didn't have it on the paper. So the way this works, or the way this problem was defined, is we had a beam. I think it had a roller, a pin, and a roller. And it had loads of value P equally distributed so that they were each L distance apart. So the total length of the beam is 3L. And the first thing we need to do is find the reactions. So I'll go over here to the pin, and I'll assume I have a force. I'll call it the shear at A. And that's positive. And I would have some axial force, which you can probably see is going to be 0. Now this is going to seem odd to you guys, but I'm going to come over here and say that this is positive shear at B. Remember our sign convention? Up on the left side is positive, down on the right is positive. So those are both positive shear forces. Okay? So far so good? Alright, so now let's find those values. So if I use right-hand rule and sum my moments at, let's do it at point A. Messed up there. Sorry, that's some of the moments at A. So what do I have? Summing moments about A, these two forces create positive or negative moment. Negative. So I'll have minus P. The first is at L distance. The second one is at 2L. And then I have my shear at B, which is creating positive or negative moment. Negative. And it has a length of 3L. So when I solve for the shear at B, I get negative P. So it means it's P, and it's actually up. But that tells me, though, at B, when I draw my shear diagram, what should the value of shear be at B? Negative P. So now if I sum forces in the Y direction, let's see what I get. So I have shear A acting up, minus the shear at B down, and then minus P, minus P. Well, I know B is that, so I can solve for the shear at A, and I get P. Sure.
So you have a pin and a roller question. Just go ahead and is it on the reaction forces or the pin and the roller?
Yeah, well, what's a little bit different about this problem is I want to eventually draw the shear force and bending moment diagram. So whenever I calculate something, I want to know what the shear force value is. So I'm assuming positive shear on both ends, but it's telling me that when I start my diagram here at A, what should my shear value be? Positive P. And no matter what it does as I move through here, what should it be when I make it B? Negative P. So you have a starting place and you have an ending point. So you have a place to start and a destination. If you can't match those 2 points, then you've done something wrong in the construction of the diagram. Okay, what I like to do next is kind of give myself a template. So I like to draw down some lines that show the outer boundary. And then I like to include lines that where I know things are going to happen. Now, thinking about shear as you move across the beam from left to right, what's going to happen as you go by underneath these concentrated loads? We've talked in class, we know it's going to change, right? So those are probably key points. So I'm going to indicate that something's probably going to happen here under this P and here under this P. I'll just add that to my template. Then I'll come over here to the side and I'll establish where my x-axis is going to be and then where my positive shear is going to be. And to help me, I usually come over here and tell what the unit is going to be for the shear diagram. That way I don't have to put the unit on every number. remember, I'm going to start from the left and move in the positive x direction when I build my diagram. Now the first step is to look at the integral relationship that says the change in shear between any 2 points is the area under the load diagram. Okay? And then it's corollary, oops, did that wrong. The change in shear with respect to x is equal to w. So I want to make sure I use these two things. So let's start with the change. Now the first thing I know is, what is the shear at A? We found it. It's P. So I'm going to start off at positive P. What is the shear at B? Negative P. So I know where I'm going to start. I know where I'm going to end. There's a lot of curves that will connect those 2 points, but there's only one that describes the variation of shear. So let's start. Change in shear between any 2 points is the area of the curve. So what's the change in shear from here to here over the first length L? Well, it should be the area under the load curve. What is the area under the load curve over from 0 to L? 0. So there is no change in shear. So therefore the value here is P. Now how many curves can you imagine that would fit through these 2 points? Well, technically an infinite number. There's only one that's right, because only one of them satisfies this relationship, which says the slope is equal to the load. What is the load? 0. And what does 0 slope look like? Horizontal line. So that's the only curve that satisfies both these relationships. Now this lands just to the left of P. What happens just to the right of P? It changes, right? And how much does it change? P. Is this a negative load or a positive load? Negative. So we're going to go from P, it's going to drop negative P, it's going to land at 0. See that? So now I go back to this relationship. The change in shear between L and 2L should be the area under the load curve. What's the area under the load curve between here and here? 0. So there's no change. What's the shape of the curve in between? Well, the slope of that line is equal to the load, and the load is 0. 0 slope is horizontal line. Now, I'm just to the left here. I go just to the right. What happens? I go past a load, so I know the shear is going to change instantaneously by how much? P. Up or down? Down. So it's going to go from 0 to minus P. Now the change in shear between just to the right of P and the right is the area of the load curve. The area of the load curve is 0. Hey, look at that. It matches. That's a good thing. What's the shape of the curve in between? It's given by this expression. It says the slope is equal to the load. What is the load? 0. There's your shear diagram. Interesting enough, you might recall, this is pretty much the same beam loading that we use in the freshman class for our reinforced concrete beams. You may recall that we had on the ends were the shear zones where we had to put shear reinforcement. This is why. The maximum shear occurs between the support and the load, as you can see from the diagram. Out here in the middle, no shear. Something else is going on there. You remember what that was? Moment. That was where you had maximum tension and compression. So let's figure out the moment is. So I feel pretty good about this. We started at a known point P. we were able to connect it to our relationships to the other value that we knew at minus p. So that seems good. Now, we use the shear diagram to construct the moment diagram. So again, I'll assume positive coordinate x. I'll assume here's my positive moment, and typically moment has units of kip feet. Now, do we know the moment anywhere in our structure? Well, let's just start here on the left side. Do I know the moment here? It's 0. Do I know the moment here? Here? Not yet. What about here? I do. What's it there? 0. So there's my starting point. There's my ending point. Now, how am I going to figure it out? Well, remember, I'm going to say that the change in moment between any 2 points is the integral or the area under the shear diagram. And of course, the slope of the moment diagram is equal to the value of the shear. So let's start here. Now I'm looking at my shear diagram to guide me to construct my moment diagram. So I'm looking at my shear diagram. You can see this section here over the first length L is continuous. So what would be the moment right here? Well, the change in moment is the area under the curve, right? So I come up here and I get the area under this part of the curve. What is that area? Base times height, right? So that would be PL, and that's positive, right? So if I start at 0 and I add PL to it, what do I get? PL. So there's my moment right there, P times L. What's the shape of the curve in between? Well, it says that it's equal to the slope. The slope is equal to the shear. What's the value of the shear right there at the beginning? P, positive P. That means a slope of positive P. And does it change? No. What kind of line has a constant slope? Right. And if you actually computed it, you would see that the slope of this line is P to 1, rise over run. Because this is value P. Now go to the next section. What's the change in moment from L to 2L? According to this, it should be the area under the shear diagram. What's the area under the shear diagram? 0. So it stays at PL. What kind of curve connects this? Well, the slope should be equal to the shear. What's the value of the shear? 0. So what kind of line is 0? Horizontal line. Now I want to get the change in change in moment from 2L to L. That should be the area under the shear diagram. So I go up and check the area of the shear diagram. It's a rectangle. Is that a positive area or a negative area? Negative. Minus P times L. So I have PL, and the change in moment is minus PL. That brings me to 0. Yay! I knew where I started, and now I've been able to get back to where I know I have to end. And what's the shape of the curve here? Well, the slope is equal to the shear. What's the value of the shear everywhere in that zone? It's constant, and it's negative. So the only curve that fits that criteria is this one, which has a slope of 1 to minus P. So here's your moment diagram. So what is the maximum moment in this beam? And where does it occur? Anywhere in this middle section. And again, relating back to the freshman class, that's why your beam would fail anywhere in between the 2 load points, which was the middle 8 inches, if you remember. Anywhere it's the weakest. Typically in the middle, but it wouldn't have to. The crack could shift around. This is very common to have a large zone of maximum moment and these large zones of shear. That's why we do that test like that. Now, if you had to do this problem by hand, in the previous method, what would you have done? You'd have had to cut this section write a set of equations, cut this section, write a set of equations, cut this section, then plot them. When you get proficient at applying these relationships from load to shear, and then again from shear to moment, you can draw some pretty complicated shear moment diagrams. And that's what we're going to do from now on. We're not going to write functions anymore for a while. Oh, I should say you can if you would like, but the ultimate goal is to get a description of the shear and a description of the moment across the structure. Any other questions? Well, I'm sure you'll have more as we move along, but I'll stop this